Hey there, it's Mrs. Tollison, and this is your review video for the Earth, Sun, Moon, patterns of motion, and gravitational forces for the upcoming test. I recommend having paper and pen next to you so that if you need to take some notes or write down any questions, and feel free to pause or rewind or go back and look at something again. All right, here we go. So the first part of this unit was basically talking about the Earth, Sun, and Moon, the system, how they kind of interact with each other. So we worked with a bunch of different models. You were supposed to develop and use a model of the Earth, Sun, Moon system to describe the cyclic patterns of lunar phases, phases of the Moon, and eclipses of the Sun and Moon. So cyclic patterns, again, it's just a pattern that repeats over and over again, a cycle. You learned about some cycles or some cyclic patterns in elementary school, like life cycle of a butterfly, maybe the water cycle. So again, the Earth, Sun, and Moon move in predictable patterns that create these cyclic patterns that repeat over time. So we're able to know what lunar phase is going to occur a week from now, or a month from now, or even years in the future, and we know what seasons comes next because these events all follow a predictable cyclic pattern that repeats over time. Other examples we mentioned about of cyclic patterns that have to do with the Earth, Sun, Moon system are day and night, the seasons, and tides, in addition to lunar phases and eclipses. For this reason, scientists can also predict when solar and lunar eclipses are going to occur because the Earth orbits the Sun and the Moon orbits the Earth in a predictable way. So the Earth orbits the Sun once every 365 and a quarter days, and the Moon orbits the Earth once every 29 and a half days, approximately. So because scientists know what those timelines are, they can make these predictions. Rotation versus revolution, it's important to understand the difference between these two things. They are not interchangeable. They have different meanings. When an object is rotating, we're talking about the motion of that object spinning on its axis. When the Earth spins on its axis, the Earth's rotation causes day and night. It makes one full rotation every day or every 24 hours. That's on Earth. It's different on different planets and on the Moon as well. The Moon also rotates on its axis, as does the Sun. An example, if you want to compare, think about a real life example of rotation. If you're able to spin a basketball on your fingertip, that's rotation. Or if a pinwheel is spinning around like a central axis on the end of the little stick that you hold it on, those are both examples of rotation. Revolution is when we're talking about one object moving around another object. For Earth, one revolution around the Sun is equal to 365 and a quarter days. It's not exactly 365 days. And that's why we have a leap year once every 4 years. We need to catch up on all those extra quarter days. So we add a day every fourth year so that it keeps our calendar accurate. The Moon revolves around the Earth once every 29 and a half days approximately, while the Earth revolves around the Sun. Okay, and we also talked about the fact that our Sun revolves around the center of the Milky Way galaxy. The Milky Way galaxy is revolving around the universe. Everything is moving all the time. And when we talk about objects moving, the orbit is what we call the path that it takes as one object revolves around another object. So why does the Moon look different over the course of the month? The Moon is not really changing shape. It just appears different over time. And the reason for that is because the positions of the Earth, Sun, and Moon are changing in relation to each other. And that's what causes the Moon to look different. The Moon is revolving counterclockwise around the Earth, while the Earth is revolving counterclockwise around the Sun, as shown in this picture. So what we observe from our point of view on Earth is constantly changing because we're seeing different amounts of the lighted half of the Moon. So as the Moon is moving around the Earth, it's being illuminated by the Sun, and we're seeing different amounts of that illuminated half, which is shown in this picture. You have a sketch that looks similar to this in your notebook. It shows that the moon is moving counterclockwise around the earth, and the arrow's not in here, but the earth is moving counterclockwise around the sun, and nothing in this picture is to scale. And you can see in this picture, one half of the moon and half of the earth are always being illuminated by the sun. Okay, the sun is shining on half of the moon at all times. But the reason we see different phases of the moon is depending upon where the moon is in its path around Earth, we see different amounts of this illuminated half. For example, here at the new moon, which is the start of the lunar cycle, all of the illuminated half is facing away from the sun. From our perspective here on Earth, when we look up in the sky, all we see is this dark part. So we don't see any of the illuminated part. So the new moon looks basically like a dark circle. It's very hard to even make out in the sky. Over here is all of the illuminated half of the moon is facing the Earth. So it appears that's when we see a full moon. Okay? Anywhere in between new moon and full moon, we're seeing some part of the lighted half. Okay? And that's what causes the phases of the moon. When we're talking about phases of the moon, we always start with the new moon and then move counterclockwise from there. So the sunlight is coming from this direction, from the right, in this diagram. This is the new moon, so we move up and around counterclockwise. Okay? And we talked about there's two kind of halves to the lunar cycle. There's the waxing part, which is when the illuminated area of the moon is growing larger, when what we see, the lighted part, is getting bigger and bigger. So we go from seeing no lighted part to a little bit, a crescent, to it looks like half of it is illuminated, more than half, and then we're seeing all of the lighted side. Then the process reverses. We start seeing less and less of the lighted half. Okay, we see a little less than the whole thing, only half of the lighted part, a crescent, and then back to nothing. So again, this process of waxing and waning, waxing is from new moon to full moon. You're getting more and more light, and the light is on the right. And then waning is less and less light, and light is on the left. And again, this kind of shows what I was just talking about. So as the moon moves from new moon to full moon, we can see more and more of the lighted half, and that's waxing. And as the moon goes from full to back to new, we see less and less of the lighted half, and that's waning. It takes about 29 and a half days to go all the way around. So to go from new moon to first quarter, which is 1/4 or 1/4 of the way around, it takes approximately a week. A little bit more than a week, 7 point something days, but about a week. Okay? Then to go from new moon to full moon, it takes about another week after that, so it's about 2 weeks. Third quarter moon, which is about 3/4 of the way around the orbit, that takes about 3 weeks. Back to new is about 4 weeks. Again, 29 and a half days is a little more than 4 weeks. 4 weeks would be 28 days. So it's kind of 7+ days to make its way to each, 1/4 of the way around. So there's lots of different possible diagrams you can see. Sometimes the sun is on the right, sometimes the sun is on the left, sometimes the sun might be at the top, sometimes the sun might be at the bottom. It doesn't matter, okay? If you understand the pattern, whenever you're looking at your diagram, make sure you just identify which direction the sunlight is coming from. Find the new moon. Here, it's, the sun, the moon, and the earth are in a direct line like this, with the moon in between the sun and the earth. That's the new moon. Find that, then go counterclockwise. So in this diagram, you go up and around. In this diagram, you go down and around. Okay? Just find the new moon and go counterclockwise from there. The other pattern we talked about is eclipses. Oh, oops, sorry, I'm getting ahead of myself. Forget that. The arrangement of the sun, earth, and moon during a full moon. I was thinking eclipses because this comes up again when we talk about eclipses. But during a full moon phase, we can see all of the illuminated half of the moon because it's facing the earth. So in this image, because it's two-dimensional, it looks like the moon is directly behind the Earth, which makes you might make you wonder, or made many of you wonder in the beginning, how can the sun be shining on the moon if it's behind the Earth? It's really not directly behind the Earth. Its orbit is a little bit tilted, so it's slightly above or below the path of the Earth. So the light from the sun is able to reach the moon and reflect off its surface. So for a full moon, it's sun, then Earth, then moon. For a new moon, we can't see the moon, and you can see that in this diagram here, because all of the lighted half is facing away from the Earth. Okay, the only part of the moon that we can see is this dark half. The rays of the sunlight can't bend around the moon and shine on the half that's facing the Earth, so it appears to be dark. Now we're on to eclipses. I jumped the gun a little bit. Eclipses occur when one body of the Earth, Sun, Moon system blocks the light by coming in between the other two bodies and casting a shadow. So phases of the moon that we just were talking about, those are not caused by shadows at all. It's caused by the relative position of the Earth, Sun, and Moon. Eclipses are caused by shadows. There are two types of eclipses, solar eclipses and lunar eclipses. Both types of eclipses can either be a total eclipse or a partial eclipse, and it just looks different from our point of view on Earth. One way that I find it easier to remember which is to look at what word comes before the word eclipse. Whatever word is before that word is what's being blocked from view, is what's something's getting away in the way of that object and casting a shadow. So for a solar eclipse, the moon is moving between the sun and the Earth, because sol means solar, anything to do with solar, that's the sun, and then the moon casts a shadow on the Earth while blocking or partially blocking the sun from view. Lunar eclipse, luna, means moon. The Earth is between the sun and the moon. It casts a shadow on the moon. It doesn't completely block it from view. It just kind of makes it a little more difficult to see. It casts a shadow on it that darkens it. This is kind of a diagram of what's happening with the light that's coming from the sun during a solar eclipse. There's a lot of geometry involved here, which you don't have to understand. But what happens is the moon, which is much smaller than the Earth, comes between the sun and the Earth. And the reason it's able to block the sun completely from view is because the sun is 400 times bigger than the moon, but it's also 400 times farther away. For that reason, the moon appears to be the same size as the sun in the sky and is able to completely block it from view. During a solar eclipse, again, it's a new moon phase, the moon casts a shadow on the Earth. There's two parts of the shadow. There's this part, the umbra, which is the darker part of the shadow. Only people that are at this kind of the tip of this cone will see a total eclipse, and that's called a path of totality. Only about 1% of people on Earth ever see a total solar eclipse when it's happening. It's a very small percentage. When we had the solar eclipse back in August of 2017 here in Massachusetts, we were far away from the path of totality. In 2024, as we talked about in class, there's going to be a total solar eclipse that's going to be viewable in like Burlington, Montpelier, Vermont. Not that far away from us. What you see during a total solar eclipse is completely different than a partial solar eclipse. People in the penumbra, which is where we were during the 2017 eclipse and where we will be during the 2024 eclipse, only see a partial eclipse. So the sky doesn't get completely dark. In both cases, you need to wear the special sunglasses or make a pinhole viewer, and then you can see what it looks like for the moon to move in front of the sun. A good kind of trick to remember the difference between the umbra and the penumbra, in my mind, is penumbra and partial both start with the letter P. So if you're in the penumbra, you're seeing a partial eclipse. So if you're in the part of the Earth that's in the penumbra, you see a partial eclipse. Only if you're under the umbra do you see a total eclipse. So here's a lunar eclipse. Again, the Earth comes between the sun and the moon. The Earth is much bigger, casts a bigger shadow. So there's still an umbra and a penumbra. You can still get you can get what's called a penumbral lunar eclipse when the moon moves in to the penumbra. Those are a little harder to even realize it's happening because it's only a very small shadow. It does not like cast a large shadow on the moon or a dark shadow. But when it moves through the umbra, you can still get a total lunar eclipse or a partial lunar eclipse. If the alignment isn't right and only part of the moon goes into the umbra, you would get a partial lunar eclipse. Many more people can see a lunar eclipse than a solar eclipse. Essentially, anyone on the nighttime side of the Earth can see a lunar eclipse as long as the moon is above the horizon, so it's in the area of the sky where you can see, and as long as the weather's clear enough to see the moon. The moon turns a reddish-brown color as it moves through the shadow of the Earth because light from the sun is kind of going through the Earth's atmosphere, and it casts this reddish-brown light on the moon. Here are some pictures. I've shown these in class. We had the lunar eclipse back on January of 2019. Oops, I just noticed this. It says 2019 twice on my slide. The upper left picture here was taken about 10:30, just at the very start of the lunar eclipse. And I kind of went out every 10 or 15 minutes or so. And this is the final picture here at about 12:05, just basically at the time it became a total solar eclipse, a total lunar eclipse, excuse me. And then it stayed in the moon's shadow, stayed in the Earth's shadow, for about an hour, and then the process reversed. It was a very cold night, so I did not, and it was very late, so I did not continue going outside after that time. So why don't we have a solar and lunar eclipse each month? Well, the reason is because the Earth and the moon don't orbit in the same plane. There's a little bit of a tilt of about 5 degrees that the moon's orbit is tilted from the Earth's orbit around the sun. It's exaggerated a little bit in this picture just to make it a little more obvious. But the only time an eclipse can happen is when the Earth, sun, and moon are lined up exactly, which happens at these 2 red dots that are in this picture, when the moon is either directly in front of or directly behind the Earth at exactly the right moment in time. So again, many times the moon is in front of the Earth, but it's slightly above the Earth or slightly below, or it's behind the Earth, but slightly above or slightly below the Earth. So we don't get eclipses then. Then after we talked about those cyclic patterns, we talked a little, just very briefly, about galaxies, just to kind of understand the idea that our Earth and our solar system are only one of many solar systems in the Milky Way galaxy. And our galaxy is only one of billions of galaxies in the universe. And again, I showed you some videos in class, and the links to those videos are on the class Aspen page if you want to review them. So a galaxy is just a huge system of billions of stars, together with gas and dust and planets and moons that are all held together by gravity. Okay? Our galaxy, which is the Milky Way galaxy, is a spiral galaxy. And you see in this picture down here, it kind of looks like a pinwheel. You've got the central area with arms that extend out from the center. And our solar system is kind of out on one of these outer arms. And when you think about these different pieces, I guess you could say, or different levels of organization in the universe is the largest level. So everything is within the universe. Within the universe, there are many galaxies. Each galaxy is made up of multiple solar systems, and each solar system has, well, our solar system just has the one star, our sun. Okay, so the star is the smallest object. Many stars make up our star makes up our solar system. There's many solar systems in the galaxy, many galaxies in the universe. So using information gathered from telescopes such as the Hubble telescope, which was launched back in 1990, scientists have been able to collect data, many pictures of deep space that show them that there are 200 billion galaxies that they can see, or that they can estimate that there are. Probably more than that, because scientists know that the or infer that the universe extends far beyond what we can see. And if we can see this many galaxies in the area that we can see, the assumption is that there are many, many more beyond that. And then finally, we're talking about gravitational forces and being able to support the claim that gravitational forces between objects are attractive, which means they pull them together. And they're only noticeable, we only can notice that there's gravity when one or both of the objects has a very large mass. So gravitational forces, or what we normally say is just gravity, is just a force of attraction between two objects or two masses. When we say the word attraction or attractive, it just means that the objects have a tendency or ability or likelihood to pull other objects towards themselves. So we talked about in class that a force can either be a push or a pull. Gravitational force is always a pull. There's no pushing away, no repelling of objects. It's only a pull. And there's a difference between mass and weight. And we'll talk more about this too when we get into the matter unit. That mass, when we talk about the mass of an object, we're talking about how much stuff is in the object, how much matter is making up that object. And we measure that on a balance, and we use kilograms. And the mass of an object doesn't change as it moves from place to place. So if I were to go from here on the Earth to the moon to like Jupiter to Pluto, my mass would not change. The amount of stuff that makes me up would remain the same. On the other hand, weight is a measurement of the force of gravity pulling down on an object. So your weight will change as you move from place to place if there's a change in gravity. On Earth, our mass and our weight are the same because, we're using the gravitational force of Earth as kind of a standard unit of measurement. And we compare other objects in the solar system to Earth. So for example, if you weigh 120 pounds on Earth, you would only appear to weigh 20 pounds on the moon, because the moon only has 1/6 the gravity of Earth. You wouldn't be any smaller, you would just weigh less. Okay, you would still be the same size, you would just weigh less. And a lot of times they talk about, on like the International Space Station or astronauts, that they're weightless. They're not really weightless. It's just they're in an area where there's what's called microgravity. The amount of gravity is so small because they're so far away from Earth, because distance has an impact, that it appears that gravity is just very, very tiny. So two factors that affect how much gravitational force or gravity there is between objects is the masses of the objects and the distance between the objects. Okay? So you have to take into consideration when you're trying to figure out how strong a gravitational force is how big are the objects, how much mass do they have, and how close together or far apart are they. Okay? So in this image, it says that if mass increases, so the bigger the mass, the greater the gravitational force. Okay, so bigger objects with larger masses exert a larger force of gravity. If those same big objects are farther apart, the increase in the distance will decrease or reduce the amount of gravitational force. So over here it says gravitational forces are proportional to the masses of the objects. So there's a direct relationship between mass and gravitational force. The more mass the object has, as I said, the greater the gravitational force. The less the mass it has, the smaller the gravitational force. So the closer together two objects are, the greater the force between them. The farther apart the two objects are, the smaller the force between them. There's a gravitational force of attraction between all objects. So when you're sitting in the classroom, there's a gravitational force of attraction between you and your pencil, between you and your notebook, between you and your chair, all of those things. We don't see those gravitational forces of attraction because the Earth is so much bigger than you that it's going to have a stronger gravitational force on those objects. So if you drop your pencil, it's not going to kind of move over to stick to you. because the gravitational force of attraction between the pencil and the ground, or the earth, is greater than the gravitational force of attraction between the pencil and you. So if there's a really large object, we'll see that object's gravitational force as opposed to a small object. So before you go on to the next slide, I want you to think about, or before you continue watching this video, you should pause this and see if you can figure this out before I show you the answer, okay? So if you look at this chart, which of the examples in the chart below would have the largest gravitational force between them? And which one would have the smallest gravitational force? Keep in mind what we just said. The two things that have an effect on gravitational force are the masses of the objects and the distance between them. So first look at mass, then look at distance. I recommend that you pause the video now and see if you can figure out and understand which of these examples would have the larger gravitational force and which would have the smallest. Alright, so starting with which example has the largest gravitational force between the objects. Start first by looking at the examples, finding the ones with the larger masses. So when you look here, we've got in all these examples, there's two objects. In this one, object number 1 has a mass of 100 kilograms, object 2 has a mass of 200 kilograms. Here again, object 1 has a mass of 100, object 2 has a mass of 200. In example 3, object 1 has a mass of 50 kilograms, object 2 has a mass of 100. In example 4, object 1 has 50 kilograms, 2 100 kilograms. So if we look at these two, you should be able to notice that both examples 1 and 2 have larger masses than 3 and 4. So automatically we know that the largest gravitational force cannot be in 3 and 4 because those have smaller masses. Okay, so now we're only looking at examples 1 and 2. Now we got to take into consideration the distance between them. So if the masses are the same, which they are in these two examples, the greater gravitational force will be between the objects that are closer together. So if we look here, the distance between these two objects is 20 kilometers. The distance between these two objects is 10 kilometers. So this example 2 is the combination of the larger masses with the less distance between them that are closer together. So example number 2 would have the largest gravitational force between the objects. So which one has the smaller? Okay. Which example has the smallest gravitational force between the objects? So you have to kind of reverse the process that we just did. Now we want to look for the examples with the smaller masses. So we saw this is the same information, examples 3 and 4 have the smaller masses. These two masses are smaller than these two. So if we're looking for the smallest gravitational force, it's going to have to be either example 3 or 4. Now we look at distance. Okay? The greater the distance between the objects, the smaller the force. So we're looking this time for the smallest masses with the biggest distance between them. So in this example, if we look here, example 3 is 20 kilometers apart, example 4 is 10 kilometers apart. So example 3 has the smaller masses and the larger distance apart. So example 3 would have the smallest gravitational force. Okay? And that is all that I have for you today. So again, please rewatch any section of this that you feel would be helpful to you. If you have any questions, come see me. And hopefully this helps you prepare for the test.